work, energy, and power. When we talk about work, energy, and power, first and foremost, we have to give the definition of work. We know that work is said to be done whenever a force moves a point of application a distance in the direction of that force. For example, a person lifting a load is said to have performed work. But on the other hand, what do you understand by the term energy? Take note that energy is the capacity to do work and not the ability to do work. We have various forms of energy. One, we have the mechanical energy, we have the electrical energy, we have the chemical energy, we have the sound energy, the heat energy, and the geothermal energy. But we're going to be discussing majorly in this class. Potential energy talks about the energy possessed by virtue of its position, which is simply a stored energy, but kinetic energy talks about that one in motion. Let's now talk about the transformation of mechanical energy. When you talk about transformation of mechanical energy, we are looking at it in two perspectives, and that is that of the potential and the kinetic energy. Before now, we know that the law of conservation of energy states that energy can neither be created nor be destroyed, but can be changed or converted from one form to another. But in this class, we're going to be talking about the law of conservation of mechanical energy. The law of conservation of mechanical energy. This law simply states that in a closed or isolated system, the total amount of energy is always constant, although energy can be changed from one form to another. Okay, I come again. I said the law of conservation of mechanical energy states that in a closed or isolated system, the total amount of energy is always constant, although energy can be changed or converted from one form to another. When we talk about the law of conservation of mechanical energy, we are looking at it from two angles. We talk about the potential and kinetic energy. So for the potential energy, we're going to be looking at how a simple pendulum bulb swings back and forth when the experiment is carried out. We're going to see a video that explains this process.
Application of the law of conservation of energy to a simple pendulum. In our earlier session, we have learnt about law of conservation of energy. Now, let us learn how law of conservation of energy is applied. Let us explain it by using a simple pendulum. Activity. Let's take a simple pendulum and suspend it from a stand. The normal position of the simple pendulum is noted as OA. Now, pull the bob of the pendulum at one extreme position B and release it. It reaches to the other extreme position C and goes on. If the bob goes from B to C and come back to B and so on, it is called as one oscillation. When the bob is at extreme positions B and C, its velocity of the bob is 0, so its kinetic energy, Ke, is 0. When the bob is above normal height, h, that is, when it is at extreme points, it has potential energy, Pe, so its Ke is 0. But when the bob leaves the extreme position and crosses its mean position, its height H is 0. Then its PE is also 0 and has kinetic energy. At equilibrium position, it has kinetic energy and potential energy is 0. And at extreme position, it has potential energy and kinetic energy is 0. In between equilibrium and extreme position, it has both potential and kinetic energy. Other than the equilibrium and extreme positions, any point in the oscillation has total energy sum of PE and KE. The sum of PE and KE always remains constant. Thus, from the above experiment, we can find the energy is transformed from potential energy to kinetic energy and from kinetic energy to potential energy. But it is neither created nor destroyed. This is called as law of conservation of energy.
But this one is for a ball to roll down. At the bottom, the track curves back up, launching the ball into the air. If the ball you use has a mass of 0.15 kilograms and the ramp ranges from 3 meters off the ground at the top to half a meter off the ground at the lowest point in the path of the ball, what is the velocity of the ball at the lowest point of the ramp and when it hits the ground after the jump? To answer this question, we need to know about kinetic and potential energies. So if that sounds unfamiliar, check out my tutorial on this subject in the Classical Physics series. Otherwise, see if you can figure it out. As we said, the name of the game here is kinetic and potential energy. Kinetic energy is the energy of motion, and potential energy is the energy of location. At the top of the ramp, before you release the ball, it's not moving, so it has zero kinetic energy. But it does have some potential energy. To find out exactly how much, we use the equation. We can plug in the mass, acceleration due to gravity, and the height of the ramp, and we get 4.4 kilograms meters squared per second squared, or 4.4 joules. Now, what we also have to understand is that as the ball moves down the ramp, the total mechanical energy is always conserved, meaning the sum of the kinetic and potential energies, in this case 4.4 joules, is constant. So as the ball gets closer to the ground, potential energy is being converted into kinetic energy. That also means that the instant the ball hits the ground, where it has zero potential energy, it must have converted all of its potential energy into kinetic energy. So the kinetic energy of the ball at that moment must also be 4.4 joules. Now we can use that to find the velocity of the ball at the moment of impact. 4.4 kilograms meters squared per seconds squared is equal to 1/2 the mass times velocity squared. So we simplify a bit, take the square root, and 7.66 meters per second is what we get. Now for the lowest point of the ramp. Let's get the potential energy first, which will be the same mass and acceleration as before, but the height is now 1/2 a meter. That gives us a potential energy of 0.74 joules. Kinetic and potential energies must add up to 4.4 joules, so the kinetic energy at this moment must be 3.7 joules. With that, we just plug into the same equation as before, rearrange, and take the square root, and we get 7.02 meters per second at that point.
It is important to note that for the law of conservation of mechanical energy, we have been able to show how it is applied in terms of its potential and kinetic energy. Okay, and here we're going to cut the curtain for today. The curtain for today, I would want to admonish you to take your quiz section serious, because your first attempt is usually the grade which is recorded. Also, your assignment session comprises of 2 parts. You are expected to do the first part in your notebook and the second part online. Do have a wonderful day. Bye for now.